In a few weeks, first-year students will be studying the periodic table in their first-year studies class. So a lot of my colleagues have come up to me in the last couple weeks and said, hey, how do you use the periodic table? What's its deal? This is how I use the periodic table. This is what I care about when it comes to the periodic table. Electronegativity can answer a lot of questions about why things act the way they act. And so I want to really, really briefly go over this with you. I know that you've seen this word before, perhaps even in high school chemistry, perhaps before that. I'm not so interested in having you memorize a definition today. What I'm interested in is getting you to be able to use this concept to kind of understand the world around you. Okay, so this is not so much a vocab. This is just kind of laying out this concept. And again, I see it as a really, really important fundamental thing that I can use the periodic table for. Speaking of the table, here is a little corner of it represented. So I'm going to compare carbon, fluorine, and chlorine here. So nucleus, electrons. All right, my carbon nucleus has 6 plus, right? 6 protons and 6 neutrons. And it's got 6 electrons. 2 of those electrons are in the core shell, and then 4 of them are in the outer valence shell. And you can kind of think of these core electrons as shielding some of the protons in the nucleus. In fluorine, we have a much bigger nuclear charge, right? So there's 9 protons there instead of 6. But now we've got 7 valence electrons. Each of these valence electrons in fluorine feels more pull to the nucleus than each of these valence electrons in carbon feels. So that's why you see atomic radii get smaller as you go from left to right across the periodic table. But again, it's not really radii I think about. It is how hard that nucleus is pulling on those valence electrons, because chemistry comes from those valence electrons. Okay? So when I think of electronegativity, I think in those terms. Fluorine, the nucleus in fluorine has a really, really hard pull on electrons, both its own electrons and whatever it's bound to. So if there is a carbon-fluorine bond here, this fluorine nucleus is going to exert a pretty hard pull, not only on its own electrons, but on carbon's electrons as well. And that's what we mean by electronegativity. In a carbon-fluorine bond, there is greater electron density on fluorine. So sometimes we draw this little weird-looking delta, which means it's not a full charge, but it's a little bit of a negative charge, and this carbon has a little bit of a positive charge. So let's look at chlorine. Chlorine has an even bigger nuclear charge, 17, right? So that must be like a black hole of attraction type of thing. Well, not really, because we're building these electrons in shells, the outer valence shell of chlorine is way further out than the outer valence shell of fluorine, right? So this is a greater charge, but the electrons it's trying to pull on are much further away, right? And as you know, if you think about magnets, magnets close to each other exert a greater force on each other than magnets far away. That's just fridge math. So again, both of these things have 7 valence electrons. And again, that's why we have the periodic system. That's why the chemistry of fluorine is similar to the chemistry of chlorine and chemistry of bromine, and so forth. But in terms of electronegativity, the fluorine nucleus can pull on its own electrons and its neighbor's electrons much tighter than the chlorine nucleus is able to, because the chlorine nucleus is just too far away from those outer electrons. So electronegativity increases left to right and bottom to top on the periodic table. That's important to remember, and that will dictate a lot of chemistry, and particularly fluorine's chemistry. So fluorine's going to make very strong bonds to things. And it's also going to have pretty weak London dispersion forces, because those London dispersion forces depend on a big, fluffy nucleus to kind of mess with by adding some external charge. Fluorine's not fluffy. Fluorine's this little ball of electrons, and it really doesn't deform when you put a charge or field next to it. Right? So fluorine, very electronegative, very tightly packed electron charge, not really able to do London dispersion forces interactions very strong at all.